much. So today I will be talking about primarily how different kinds of technological paradigms are affecting how we design and interact with the environments around us. And maybe a lot of that content might not necessarily be directly related to architectural design per se. So in terms of majors, are there any architecture students in the room? Okay, there's like a few. Well, I mean, I started my teaching career teaching architecture at Woodbury, so it's kind of nice to be back in a way. That was a long time ago, but a lot has changed since then. And lately, I've been starting my lectures with this gift that I found online, which is demonstrating a person pretty much immersing himself in all kinds of popular technological junk. And you know, in this image, you're seeing the DeLorean from Back to the Future as almost like a kind of an aspirational set piece next to like the hoverboard, and then there's like a selfie stick and a VR headset and a drone. So all these things that probably just entered our lives as toys that carry very complex pieces of technology, but they were not known to us like 5 years ago, maybe 10 max. But there currently you can go to CVS and buy a VR adapter at least to put your phone in. But also a lot of these technologies haven't really caught on. So even though they're being mass produced and they can be found everywhere, they haven't really fully infiltrated a lot of the activities of everyday life. So the reason for that, I think, is many, but I think a lot of that has to do with certain ways in which technology infiltrates daily life through commercial objectives. And a lot of these commercial objectives, I would say, are to a certain extent self-fulfilling prophecies. So if you see something in science fiction, it almost creates an interest or a market for it. And once that market is created for it, there's a certain scientific set of explorations that are geared towards making that particular paradigm happen. And I would say that VR is one of them. Every time I'm having a conversation with somebody who's a little older about VR, and then tell them, oh, we've been working with VR, and they're like, oh, VR has existed, for like 30 years. I mean, they say that, but the thing is that the idea of VR existed for 30 years, but the actual tools to create virtual environments that could be fully experienced only existed for the last 4 or 5 years. So again, I think it is important to understand the relationship between science fiction and future projection, and how that influences actual science, and how that influences design, and what are the things that, in a way, kind of allow us to think about those paradigms as things that resonate in popular culture and philosophy. So a lot of that has to do with certain popularities of concepts that, again, have existed, I believe, for many years, such as robotics and artificial intelligence. And the way that those concepts have been, in a way, turned into philosophical notions have been through, again, techno-scientific writing. So if you think about concepts like transhumanism and posthumanism, they are actual consequences of discourse that is happening through the sciences and not through literature or philosophy. And I think it is important to realize that, because I think it indicates a certain kind of split between social sciences and sciences that realize that there's a certain kind of philosophical and social implication to some of the inventions, And I think almost the sciences created their own social science discourse that has veered away from the actual discourse of philosophy and sociology and what have you. I would say that lately those two things are merging together. The reason why I'm giving this long introduction is I think for a majority of you who are, I believe, computer scientists, to in a way understand and start developing a certain kind of sensibility towards those notions in order to realize that the kind of split that has happened is actually starting to disappear. And I believe that those kinds of different intentions that are evident in different social science practices are in a way being combined. And the reason for that is because a lot of these devices that I am going to be talking about as environmental applications of technology are becoming true. So I named this as the cyber-physical architecture. The reason why I name it that way is because it in a way kind of relates to a lot of the tools of the fourth industrial revolution, or Industry 4.0 as the most popular name for it. And I think it indicates a certain kind of, it indicates a different kind of approach for planning and then designing environments. And it almost always has to involve an equal level of sensibility towards a technological infrastructure and an architectural infrastructure simultaneously. So what I mean by that is how transhumanism and posthumanism as philosophical discourses are going to be affecting environments. And the reason for that is because the environments are becoming context aware, meaning environments are becoming cybernetic ecosystems of humans, sensors, and robots and other artificial beings. As a consequence of this, space is becoming an extension of the human body. I believe that there are other people that are exploring this more in depth than I am, especially towards wearable technology. I'm sure you're aware of some of these people, but I think it's a part of the same problem, that the body is no longer the only actuator of affecting change in the environment, that certain capabilities of the body can be bypassed through other technological means. And also thinking about interface design and architecture converging together, meaning the kind of the two-dimensional aspect of the screen or the phone is in a way starting to disappear, and the interfaces are becoming more environmental and context specific. And the notion of artificial intelligence in a way manifesting in two different ways in design discourse, one of them being AI or machine learning systems being used for designing buildings or environments or new experiential applications, or they are being integrated into environments so that they become more interactive or responsive. I think those require two different kinds of applications, and they require two different types of infrastructures. And also what it usually means for production is that we're moving on from a kind of a numerically controlled digital production system into a generative fabrication system, where machines and tools that are actually tasked with producing components of environments or other kinds of design objects are given more autonomy and leeway in the process of contributing to that design as they are fabricating. And the last thing that I am going to talk about, which is probably going to take up a lot of my time, is about how virtual and augmented reality can be perceived as a synthesis of perception and representation, and how digital environments can exist in their own right so that they're not just representations of environments that could be produced in the future, but they are actually the product. They are the actual environments that are designed to be experienced. And there are different design rules for that. There are different technological and programming related I would say, formulas for that. That requires a different kind of understanding and approach compared to designing a building. So all this kind of leads me to this thesis about spatial intelligence, meaning spaces gain intelligence through a combination of sensors and scenarios, meaning sensors representing means of collecting information from the environment, scenarios meaning that information that is being collected is being grouped in order to create certain kind of effects and outputs and functional responses. And spatial intelligence also implies that intelligence environments develop autonomous and semi-autonomous reactions to people, the environment, and other objects. And they're formed by a combination of digital and as well as physical objects. And they have an ability to change based on various practical, social, and cultural contexts and purposes. So in this kind of ecosystem, this cyber-physical ecosystem, the way we view architecture could also be, just a digital environment. It doesn't have to be a physical environment, or it could be kind of an allegorical or metaphorical environment in the same way we talk about a computer architecture, right? We're not talking about an actual building, but we're talking about the way in which different systems integrate, the different systems and programming methods actually are interfacing with each other, and how those different things could be experienced together. So as a part of this ecosystem, sensors are a part of it, robotics are a part of it, algorithmic design systems are a part of it, electromechanical systems, smart materials, digital interfaces, VR, AR simulations and overlays, other media technologies such as media facades and what have you, and wearable technology as a way to actually collect information from the occupants. So all of these different things, I would say, are creating the cyber-physical architecture. So I will talk about how this topic is being explored in my lab at UCLA, which is a part of the IDEAS platform, and how it is being explored in the office in various projects. I excluded the super architecturally specific projects and tried to focus on ones that are more centering around technology. So, in the lab at UCLA, we are primarily focusing on this relationship between presence and action, and how we can occupy cyber-physical environments, whether those environments are fully physical or fully digital or somewhere in between. And we're also looking at it topically as a kind of this range between work and play, meaning environments that are geared towards productivity and collaboration versus environments that are focusing on entertainment and leisure time. So within that range, we're looking at multiple different kinds of concepts and devices. Like, in the spectrum of presence, we're looking at virtual reality, augmented reality, or other kinds of extended reality or mixed reality applications for the purposes of either experiencing a virtual environment or for the purposes of telepresence. And then in the physical spectrum of actually initiating action and change in physical or digital environments, we're looking at robotics, sense-based interaction, and again, with the consequence of telepresence. So I will go through a few projects about what I mean by all this. A few, obviously these are group projects that are collaborative in nature amongst the students and the faculty. These couple of examples are from the course that I taught called Architectural Intelligence, where a group of architecture and media arts students were tasked with creating cyber-physical ecosystems through various combinations of devices and topics that I have provided for each team. For example, for this team, I told them that they have to have a physical structure that is designed to move, that is designed to transform, which would have to be attached to a robotic system. And then another robotic system would be in control of a media application. In this particular scenario, a video projection mapping system. And then the entire system would have to be controlled by a sensor. In this particular instance, I gave them a leap motion sensor. So what is being created is a full-scale architectural physical panel that is being actuated by a large-scale industrial robot. Meanwhile, the other robot is real-time mapping a video projection onto that board, aligning it real-time through a camera feed that is above it. And meanwhile, the whole system is being synchronized through the leap motion. So through the hand gestures, you can not only change the physical properties of the architectural panel, but also the digital content that is being projected on it. So the purpose of this project is to think about an architectural system where you can walk in and you can not only change the physical parameters of that architectural environment, but also the ambient properties of it through lighting and media. Another project from that same group was this other silicon panel that is greeting you and moving towards you when it sees you, and then changes color when you touch it. And then we moved on to more specific scenarios where I asked the students to design a pavilion for the South by Southwest Festival and create a virtual reality scene that is supposed to represent the pavilion. And each pavilion scenario was different, and it had to be transforming physically based on a biofeedback from the occupants. So in one scenario, the performer, a DJ that is supposed to perform in the pavilion, has an EEG headset and the environment is changing accordingly. In another scenario, certain kind of ambient data is being collected from the occupants of a dance party, and their body temperature regulates the amount of volume of an inflatable environment. So there's multiple different kinds of parameters that affected this kind of continuity between feedback from human occupation and how a building can transform physically and digitally in response to it. So obviously there's a lot of programming schemes that they have to perform in order to make this happen. And in many cases, the way that these manifest in the studio is that they have to build a prototype for a portion of it to represent how the actual physical thing is moving and how it is being controlled through a sensor interface. And then they create an overall simulation in VR that represents the entire system. And then they have to make digital animations in order to, again, represent the entire system. So we also did other experiments where we are controlling real-time robotics through virtual reality interfaces. And these are all handmade robots in a way. And right now we are working on our proprietary software to control industrial robots from VR directly. And the purpose of this is to create, a more streamlined relationship between the digital and the physical worlds. And this, in a way, kind of also is at the very center of why we are exploring virtual reality. We explored virtual reality in two different ways over the last 5 years. The first is, again, a representation of a proposed design so that we can, in a way, understand and measure certain performance-related aspects of that design prior to the design being built. But another one is about creating VR interfaces that are environmental and experiential. And these next few examples are those. For example, this interface has the capability to go from object to space. So you can, through zooming in, turn something that is the size of an object into an environment. And then through, again, other hand gestures, you can change the physical properties of that environment from transparent to translucent to different colors. And another example of that is, again, this kind of non-traditional architectural approach that is geared towards questioning certain kind of given parameters of architecture. In the first scenario, if we were exploring scale, in the other scenario, we're exploring presence through teleportation. So you can actually move through different parts of the design through teleportation, and you can actually change the physical properties from opaque to transparent in order to determine where you want to move within that space. Another version of it is that there is no actual built environment, but your actions are creating the environment. So in this particular instance, there's a game-like interface that are creating enclosures through gestures. So certain kind of gestures, physical gestures, equate to certain methods of construction, so to say. And then through an interface, you can have a direct feedback of what you have constructed so far in order to navigate through that. And then we looked at alternative methods of interacting with environments. In this particular instance, certain voids are being created and portals are opening based on your gaze rather than your gesture. So wherever you're looking at becomes an opening. Or if there's an opening in there, it opens up when you look at it so that you can actually kind of move through that environment. And then lastly, this notion that you can actually design in VR, but not in the same way that you design in, let's say, an interface like Oculus Medium or Tilt Brush, but there's actually an architectural palette that is predetermined. And then through, again, certain gestures and decisions, the user can create a prescribed type of environment within a certain set of design parameters. So these kinds of explorations, we also wanted to, in a way, come back to the physical world a little bit more and create real-time interactions between objects through robotics. So we created a number of different schemes where we have these like either handmade robots, or you were using the industrial robots at our disposal in order to actuate systems that are designed to move or that are designed to interface with other objects. Like in the example of the soft grippers, the design problem was that we would give the student groups an object and we would ask them to design a soft robotic gripper that is only designed to grab and pick up that object, so that there will be a relationship between the electromechanical system and the design of the object directly, so that it becomes a very specific design problem. In other systems, which are extensions of what I described earlier, how could we use VR as a method for human-robot collaboration? So in one example, you're seeing you are teleported inside the industrial robotics environment by controlling one of the robots real time from the VR interface. Meanwhile, the other robot is doing a prescribed automated set of motions that are repetitive. So you have the capability to intervene into an automated process as a human as it is happening. So what are the boundaries of human-robot collaboration? How can we leverage different qualities of humans versus robots in an industrial production environment? So those are some of the questions that we have asked. Another set of questions were, what if architecture itself was a giant robot? Like, what if architecture could transform like a robot according to certain environmental factors? So the students were tasked with creating enclosures that are interactive through different sensor interfaces. And lastly, this kind of notion of controlling the environment through VR and telepresence. We asked every student group to create first a fully interactive digital virtual interface, and then create a copy of that interface as a robot in the physical world. So each time you're initiating a change in the VR environment, the physical object itself is transforming in real time. So as you can see, maybe I can just try to pause this in this particular moment, which I think could be a little bit more interesting for, where is it? Some of you, yes. Oops, how can I freeze it? I just want to show you what is going on behind the scenes here, because there are so many things that are interfacing with each other, right? Like in this particular project, they were taking real-time Facebook data in order to transform a physical model. So in order to make that happen, there's an interface that is capturing the data from Facebook, feeding it into Unity. The digital model itself, through Rhino and Grasshopper, has a set of parameters that are being interpreted through GHAL and then being fed into Unity. There's a C# script that is working within Unity to integrate these different two sets of data together. And then there is a real-time animation that is being synchronized, that is fed from Maya, that is projecting a Turing pattern on the exterior of the physical model. And then there's leap motion that is in a way kind of initiating all these different physical changes. So when you do something physically, it actually feeds information back into Facebook as if it is an interface, an abstract interface to interface with Facebook. And then all the physical computing is, from Uniduino going into Arduino, and then the physical model is transforming. And all this stuff is being coordinated through one single file in Unity. So if you think about it, there are physical computing aspects that are being synchronized from data from the internet, and then there are other design-related parameters that are more ornamental that is following this information and then feeding another physical system like the projector to create a real-time pattern that maps on top of it. Maybe if you see it, that could be a little.
What are you using for projection mapping? Does your students use Touch Designer?
Either Touch Designer or Isadora. But what we're trying to do is we're trying to get away from prescribed systems as much as possible, and we're trying to do everything real time, so that you in a way create set of rules and allow these different systems to interact with each other. And in that regard, I think Unity is really amazing because it really allows you to synchronize physical and digital data in an interactive way. And it is, I would say, a system to design behaviors rather than designing forms. And I find that to be incredibly compelling and a point of diversion from a traditional way of thinking about computational design. By the way, if anything is unclear, you please feel free to ask me questions as I go along. But if I can find this project, that would be really great. Not this one. Anyway, I couldn't find it. It's the one before. Should be this one. Yeah, you see, this was a project that I was telling you about. That there's a physical model that is transforming, and then there's a real-time projection that is happening to it that is transforming. And also, this entire system is being controlled through leap motion, as well as changes that happens through your Facebook data. So if you move your hand, it basically translates to a particular action in Facebook, like such as liking somebody's picture, or uploading a different kind of media into your profile, so that there's a direct bridge about a physical action versus a digital output. And then this interface becomes this pet in a way to interface with your Facebook account. Anyway, so we did that for Twitter. We did that for like basically majority of the social media applications. How can we turn them into physical interfaces was what we asked in that particular studio. So this was all the stuff that happens in the lab. And I want to show a few projects that are related to, again, a lot of this work, or the principles of this work that is happening in my office. The first project probably is the project called Cerebral Hut, which was something that I completed 5 years ago, which is a physical environment that has an electromechanical system within it. And the entire system is being controlled by an EEG headset that measures your concentration levels. So the sensor that you wear as a helmet, as you're seeing, being a part of the audience, is measuring your concentration levels and allowing the environment to physically transform based on this data. Another project, which was a pitch for an electronic music producer called Actress, was to take his music real time into a modulated, robotically assembled system so that it could be assembled and disassembled as a backdrop behind him based on the real-time data that is aggregated from the music as a part of the performance. Another project that was a pitch at LACMA's Art and Technology Lab was to create a floating canopy system that is actuated by drones. As a first version of it, it would cycle through different kinds of architectural enclosure types. But as a secondary system later on, it would start interacting with real-time sensor data. Initially through EEG, and then later on through a more advanced motion capturing system that would allow the system to, in a way, dance and collaborate with an actual performer. So those, I would say, are the more like kind of physical performance related projects. And some of the more digital AR, VR related projects is the first one being the augmented reality intervention that we did at the Venice Architecture Biennale 4 years ago, where we had a treasure map and a specific augmented reality app that you would download, and you would go through with a phone or like with a tablet, you could go through the entire exhibition designed by Rem Koolhaas and unravel digital relics from projects from the 90s. So all these projects were from prominent architects that we collected based on their projects from 90s onwards, and you would be able to upload the actual original 3D model of that particular project, and it would exist physically in that environment. We even managed to get the first copy of the VW bug, and also the first 3D model of the teapot from its actual source. And then we had to kind of translate that file format into OBJ in order to insert it into the augmented reality environment. I would say that those projects are more in the art installation and speculation territory. Just to move into a little bit more practical territory, we participated in NASA's open call to design the first human habitat for Mars for astronauts, which was a competition that they opened 2 years ago. And you had to create, also, you had to write a white paper to propose a methodology for 3D printing this habitat based on the indigenous materials on Mars. So our strategy was to, rather than thinking about the traditional methods of regolith 3D printing, which is very similar to concrete 3D printing, we decided to actually go in a more high-tech route where very conventional machines would collect, grind, and heat and fiber basalt rocks, which has very similar properties to carbon fiber. And then, again, very conventional knitting equipment would create sleeves and panels or like sheets of woven fabric. And then these pipes and sleeves, as you're seeing in the end effector prototype on the corner over here, would extrude the pipe, and as it is extruding, it would spray a type of resin on it that cures through exposure to ultraviolet light. And because there is no atmosphere on Mars, the UV radiation on Mars is actually quite radical. So what would happen is that the moment that it is coming out of the end of the effector, it would freeze. Therefore, it would create this kind of woven structure that becomes structure and conduit at the same time. And it would also be high performance because it's practically the same material that is being used for space shuttles and satellites. So we also, in order to convince them, we were tied for the third spot with the European Space Agency in this competition. And we also created a VR simulation for them in order to demonstrate to them what the structure would look like. Because the case that we were building for the architectural language of this thing was that once this actual thing actually happens in 15, 20 years, it's probably going to be broadcast on television. It's probably going to become like a very highly visible event. So we need a type of architectural language that can capture the imagination of different generations of people and sustain that energy in order to provide sustained support for the project. So we created also this interior virtual reality scene, which demonstrates what the cabin would look like.
Was the topography of Mars, was that provided to you?
You had to propose where you want to land.
And then generated from an image.
Exactly. So we created the environment, yeah. So based on this relationship, we got invited to create a landscape feature for the JPL campus in Pasadena. And based on our conversations and our observation, none of the people actually really enjoyed working in their cubicles. And most of the time, all the work areas and offices were empty. People were either sitting outside, or they are meeting in a room with a group of people and collaborating, or they're in a lab. So nobody is really actually, when they're working individually, nobody is at their desk. So we thought, why don't we create a series of different functional semi-robotic landscape features? And in this proposal, we proposed a robotically actuated carbon fiber canopy that provides different levels of shading and privacy for 4 different functions that could be coordinated through the calendars of everybody's digital, information. So you could say, oh, I want to have an outdoor meeting with 5 people at 3 p.m. And based on that information, the robot would shade that particular work table depending on the position of the sun, so that you could also have a private and shaded meeting outdoors. Same would apply for the, let's say, the small amphitheater type situation where you can say, I want to make a presentation, and then the geometry of the canopy would be repositioned in order to provide that kind of enclosure and what have you. So these were like the different scenarios that we proposed for this landscape feature. And based on this proposal, we were asked by Coachella last year to pitch another proposal for them. And similar to this, there are previous project. There are 3 carbon fiber leaves or like petals, I would say, that are robotically actuated, and they are positioned on 3 pillars within a kind of a tensile structure, and then there's video projection mapping on the exterior of this structure. So what is happening is that during the day, the structure is low to provide a maximum amount of shading. Let me see if this. So you're going to see that there are like basically 3 projectors that would have to be synchronized to provide a spectacle for the evening. And during the day, it moves according to the sun path in order to provide maximum amount of shading underneath. So it moves very slowly during the day, and it moves much faster in the evening in order to create this kind of more interesting visual spectacle. And the patterns would, in theory, based on the proposal, also work with an augmented reality app, which would provide information. Okay, this is going nuts a little bit. Which would provide information on set time, so you could hold your phone, and that particular pattern would call out different set times about different artists in different directions, so that it becomes this kind of a navigational device also in the landscape. So moving on to the last project that I'm going to talk about. I think I'm running out of time, I guess.
Oh, perfect. Then actually, we'll have a bit of time for questions.
Okay, cool. Is this project called Cypher, which was made possible through a grant from Google's Artist and Machine Intelligence program. The idea of the project comes from this I would say lifelong ambition of mine about exploring the relationship between sculpture and architecture. And usually for me, technology is a way to create why is my computer going nuts? Is a way for me to create that bridge between sculpture and architecture, or that kind of interchangeable relationship of scales. So the project itself, in the form of a sculpture, is combining soft robotics, machine vision, electromechanical systems, and the sensor array. And it bridges the physical and the digital worlds through real-time translation of actions from the digital to the physical through robotics and VR. So it allows you to interact with the project either as a sculpture or as a form of architecture, which I'm going to explain in a little bit. And then through machine learning, it develops autonomous behaviors the more it gets exhibited. And it also becomes this kind of platform for ongoing research because it has multiple sensor systems embedded in the sculpture, so we can through time figure out how people are interacting with different sensor systems and also different interfaces. So the way it works is that in the section of the sculpture there are multiple electromechanical components. There are various linear actuators, there are various sensors that are embedded, and the entire sculpture is tethered to a VR headset. So the moment you put the VR headset on, you're teleported to the interior of the sculpture, as if you are like a small person in it. So the sculpture, just to give you kind of a preview about how we built it, it's built up of extruded aluminum frame with 3D printed steel joints. And one half of the sculpture is 3D printed with a carbon fiber thermal plastic. The other half of it, where's the other half of it is one second. I'm gonna change the order of this real quick. The other half of it is made out of silicon, and it's made out of these silicon clusters that are pneumatically inflated based on two sensor inputs. One of them is an embedded infrared array, and the other one is a LiDAR that is on top of the sculpture. So the sculpture can detect your position up to 40 feet away, and then it can start changing its global geometry. And then the closer you get, it can actually change local geometry based on the input that it gets from the infrared sensors. And you see that the silicon panels that are actuated by linear actuators look like this. And the entire system, as you can see, is made up of hundreds of parts. The bottom half is solid 3D printed. The top half is silicon inflatables that are poured into a 3D printed set of molds, and then the linear actuators allow for the global geometry of the sculpture to transform. And then locally, as I demonstrated, the small clusters inflate and deflate. And as I said, there's a big LiDAR on top of the sculpture that collects all kinds of information, but primarily a point cloud information. But it also can differentiate between different types of objects. So it differentiates between a wall and a person and a cat. So whatever we trained the machine learning system to recognize, currently it is trained to recognize humans based on a certain height. So, as I described earlier, once you put the helmet on, you are in a way kind of teleported inside the sculpture. But this is not only a kind of a visual thing. Because of the interface, the control interface on the helmet, your hands and body are also present in that digital environment. So when you are doing certain hand gestures, you can control the virtual reality simulation, which would in real time change the physical properties of the robot. So each time you change the VR, the robot changes. And each time somebody changes the robot, the VR changes. So there's a direct correlation and continuity between the digital and the physical worlds. So there's also kind of a physical feedback in the moment that you put the helmet on. And then, once you put the helmet on, you can see your hands digitized, you can see your body digitized, and then your hand gestures are actually transforming the physical environments. So I will end with the full video of this project. So as you can see on the exterior, there are 36 different infrared sensors. And then on top of it, there's the LiDAR. And then the linear actuators change the global form of the project, of the object. And once it sees you, then it greets you. And then when you get closer to it, based on your proximity to it, you can locally interact with it by inflating and deflating certain clusters. And then based on the position of your body, the global geometry of the project transforms as well, fully interactively. And then once you put the headset on, which you're about to see, as I demonstrated earlier, it changes you physically or how people see you. And you can no longer see the people around you, obviously, but you see a digital version of you. And in this digital simulation, you can, through your hand gestures, change that digital environment, which in real time changes the physical object, and whatever changes that occur to the physical object through the sensor interface changes the virtual reality scene real time as well. All right, so in my talk, I tried to demonstrate to you the relationship between, I would say, the physical and the digital worlds, and how we can use programming techniques and also different kinds of technological interfaces to travel in a way between them or to occupy them simultaneously. And that is in a way the for me a kind of a passion. So I'm more than happy to answer any of your questions. Thank you very much.
Thank you.
How long did that take you to do?
Like a year and 3 months. In the beginning, we had 7 people working on it, and towards the end, we had 3 people working on it full time. So it took a long time. And it's still not like a washing machine, It's not. It's a prototype, so there's still a lot of room for improvement. But also, we did certain things that have never been done before. This kind of real-time interaction between digital and physical through VR is something that we just kind of had to actually program. And or at least at the time that was the case. Towards the end of it, certain assets occurred in the asset store, which would have been incredibly helpful if it was a year before, but that was not the case.
What's really impressive about this project is how everything, you were able to integrate everything with the physical object, and I think most importantly the LiDAR itself, because that usually is kind of the one part that usually stands out, and you kind of see the same type of LiDARs that appear in a lot of robotic competitions or projects. So I'm curious how much of the design was influenced by that specific type of LiDAR that you ended up using, or if you could kind of talk about from your proposal, because we saw some of the projects that were more kind of they were in the pitch phase and some of them were executed.
Yeah.
Because that's something that I think is very interesting for our students as they're going towards more kind of understanding how their projects and their research could fit into a larger research.
Yes.
So if you can elaborate on that.
Well, I will, just to answer your question first about the LiDAR. The initial proposal, actually did not have a LiDAR. It had 5 Intel RealSense depth sensing cameras that were organized in strategic places. But then we realized that because the cone of vision, the field of view of those cameras are actually not very generous, there were a lot of blind spots and there were a lot of overlaps, and it was collecting way too much information, a lot more than what Unity could handle. And at the time, when we started, Unity could handle only 1 camera at a time. It was not capable of handling 5 cameras and information from 5 different sources all at once. It would just crash. And we were like, okay, let's try to get a planner set of information parameters that would allow us to track any object in space, and then we can then, in a separate EXE running simultaneously, do a machine learning system that would allow us to differentiate between what information should be taken into consideration and what shouldn't. Because we realized that we really reached the limits of what we could do within Unity with the existing CPU, GPU power that is available on the market. Nobody's trying to integrate this much information all at once in a singular system. So that's when we actually started looking into LiDARs. Again, like a lot of the more industrial scale uses of them, they again collect way too much information, a lot more than what we needed. So then we kind of modified the physical design a little bit so that the LiDAR could be integrated into the geometry of it. That's how we ended up with this kind of baby Darth Vader type of situation with the helmet. And in order to kind of conceal it within the overall geometry of the system. Because that kind of continuity is also very important. And one of the premises of the project was that it would always do any kind of tracking inside out, that it would, as an object, sense its environment rather than a set of sensors established in the environment would position where it is. So even the VR headsets that we're using, which is Windows Mixed Reality, is inside-out tracking, rather than relying on, let's say, an outside tracker like the HTC Vive or the Oculus. So that it's an object that can see its environment rather than processing information from external sensors that see it. So the project technologically, I would say, transformed quite a bit as we hit a lot of roadblocks, because our goal was to load this thing up like 300%. And if we end up with like 90%, then we're good, right? And with that 90%, we can continue using this as a research platform. So a lot of the infrared sensors, for example, are not useful because there's no inflating cluster next to them, but we included them and we embedded them anyway in order to collect information, and maybe that information would eventually make sense or reveal something interesting about people's ways of interacting with certain kind of visual data, tactile data, and how they position themselves around the sculpture. So there's a lot of redundancies in the system in a way.
But I mean, going back to use of LiDAR and because ultimately it's used for navigation purposes,
Yes.
Analysis. I mean, I think with this setup, and then I can start to see how this could be. I'm assuming you're just doing planar scanning with the LiDAR.
For some parts of it, yes, but for other parts, there's a small slice that we're getting for. If we want to do object recognition, we have to get a silhouette. In order to get the silhouette, we kind of wrote another script that limits, like that collects all the information and deletes it immediately, because that like point cloud data becomes so heavy afterwards.
But I could kind of start to see how then this could potentially start to be then a mobile element, so then there's more of a condition recognition.
Yes. I mean, ultimately, this is a sculpture, right? So it's not meant to travel, like, or like, it's not meant to, like, it's not a vehicle. It is moving, but it is moving in a static place because of the way in which it is supposed to be experienced and exhibited, right?
But
So
I think my comment is more about, I mean, the interest here is about high resolution environmental awareness.
yes.
And in a sense, and ultimately in relationship of the sensor to the object, usually either the target is moving, the object is moving. So that I think in this case, with the setup and kind of maybe over engineering it, you are kind of alluding to other type of users.
Yes, of course, yeah, for sure. I mean, the redundancy of data is obviously implying that, number one. And also number two, I mean, the LiDAR is again like an overkill solution for like such a simple set of, I could just get like high range infrared sensors, like 5 of them or something, and then just like put them on the base, and then that would give probably enough data, because a lot of what we're trying to do is actually trying to reduce the amount of data that the system has in order to make it more efficient. Like we're doing that with the machine learning system too. So the machine learning is doing 2 different things. One of them is like because of the way that your position changes, you are ending up in certain zones that initiate like the motion of the linear actuators and the inflation of the clusters, right? So, but we cannot have a situation where you're on a border and it goes like, because like it is not really measuring the amount of pressure that these clusters are receiving. And eventually it might just like keep inflating and inflating and it might just pop, right? In order to prevent those kinds of damages to the actual sculpture itself, what the machine learning is doing is that it is accumulating data based on how people are approaching it, moving around, and creating an average. And then it is making a presumption about where you're going to be moving next. So then it'll basically activate a predetermined scheme so that it becomes a more predictable set of motions for the electromechanical system to handle.
So I'm coming from the architecture major and also taking some computer science class, and we did some VR stuff. And then I realized what is kind of incredible with your project. Is it like feeding real-time data from Rhino to Unity? And then is that bridge you're using the G-how you mentioned in that graph? Is that like all you need to have like Rhino communicate to Unity?
Well, in that project, yes, but in this project, I don't have such information. Like because in order to get a high resolution environment within Unity, you kind of have to have predetermined geometry with a certain amount of polygon counts, and it has to be lit up properly. You cannot have real-time geometry feeding into a highly complex textured environment like this. But for like more simpler projects, we did have a real-time bridge between Grasshopper and Unity through this thing called UDP, which is a communication protocol that allows you to interface with any kind of outside inputs and outputs.
Students here are trying UDP and OSM
Okay.
protocols, but we touch designer.
Okay. Yeah, I mean with UDP, basically like this entire project is communicating with all the electromechanical systems through UDP. There are different EXCs that are running the linear actuators based on the protocol of that manufacturer of that linear actuator. So we are just making a bridge through UDP between those EXCs and what Unity sees those EXCs as, so that it can send specific IOs to particular channels that are open, because ultimately, like we're not building our own robots, right? We're not building our own linear actuators. We're buying them, we're integrating them, and we have like controllers to control them, right? I mean, but what I would say, I would imagine that a lot of what you're probably doing is, if you're working with physical computing, is going to be Arduino. It's just that with us, we needed something a little bit more industrially robust. So in many cases, we had to work with the controller systems of the manufacturers of, let's say, the linear actuators and what have you. But UDP is great.
Do you just work with Arduinos or with Raspberry Pis as well?
I think, I mean, most of the times we're using, at least in the class, with Arduinos. Like I have like one or two students that kind of put together their own Raspberry Pis and what have you, but I feel like there's just, yeah, exactly. Yeah.
Also, I'm kind of interested in connected architecture, and that's kind of my topic for my degree project. And I see your proposal for Coachella. And then in such big scale, would you consider like, instead of like an installation, can it like be some kind of like housing project, like with moving parts? And do you think like maybe in the near future, is that possible to build something like that, like within California? Like what about the coding, like the city code and stuff like that, like building code?
I mean, I would say that usually there are two applications of new technologies. One of them is about defense, the other one is entertainment. And then it becomes like from those two sectors, they become popularized, you know? So obviously this is primarily designed to be a certain kind of spectacle, right? And it doesn't have any kind of functional purpose. But my objective was to, in a way, collapse this barrier between what is perceived to be architecture versus what is perceived to be a digital environment. So through these kind of media applications, what I'm trying to advocate for is that architecture is not necessarily a physical medium. It's not necessarily a static medium. It can move, it can change physically and digitally and through media. So that is in a way I would say what my kind of ambition is. I don't think that it is applicable to all kinds of functional parameters or applications. Like I don't think that housing necessarily is an application that needs to physically transform. But there are many other applications that I think are, like such as like a theater, an environment that needs to accommodate 1,000 people versus 300 people that are sitting versus standing, Those kinds of things, depending on the program of that particular architectural environment, can physically transform. And they also need to transform through media as well. So I think there are certain programs that are naturally appropriate for this kind of paradigm, and there are others that are just like simply not necessary.
I originally was going to ask, normally, how often do you find yourself working individually on these? But after seeing the complexity of the project, I think I'd rather ask, how diverse is the background of all of the people that end up working? Because this is definitely not something that I can see, someone working on by themselves as extensively as
No.
it is.
No, there's no way that it would probably take me 3 years on my own, one person. But at certain points, like the physical fabrication components, it just is just a lot of daily labor, right?
Mm-hmm.
You just have to do. And also just welding, soldering little things. 36 clusters that are pneumatically controlled, that have infrared sensors, that have interface with an I/O, that have are connected to the power supply. Each one of them require at least 15 to 20 wires, and they just have to be soldered or connected together and whatever else. So it is a huge team effort, and also the programming inputs. There's VR, there's physical computing programming. Pneumatic controls are different than electromechanical controls, so there's a huge variety. But surprisingly, everybody in the team had architecture training only.
So would you say they were learning off of each other as well?
Yeah, of course, yeah.
But I think it goes back to the workflow diagram that you showed earlier. I know it was for a student project,
Yeah.
but ultimately, I think what's interesting about the work that you're showing, some of it is about interoperability and creating customized workflow when needed. But then sometimes that kind of just takes the back seat, and it's more about the final product. And I think being that this is an applied computer science program, but in media arts, I think our students find themselves often in this role that sometimes it's about the final kind of end result and the content and kind of understanding kind of the placement of the work in the discipline. But the reality is that often it does become about finding not only platforms but workflows that are suitable, and definitely as we go towards thesis, that becomes really important. But I guess on that last question, how do you kind of planning this workflow and more importantly being able to that process as it allows you to break down the tasks and kind of be able to work in teams, If you could talk a little bit about that in the context of studio studying and studio projects, do you allow them to maybe, or do you ask for them to start from the workflow process? Or is it more conceptual design and the workflow is something that's emerging?
I mean, it varies. Like, I would say that in the office, it's usually, tried and true workflows that come from the lab. Like, I wouldn't do R&D in the office. I would do research and development at the UCLA lab, and then if a certain kind of computational workflow actually works, then I would decide to do a project on it in the office. Like, for example, the Cypher project and this direct control between electromechanical system versus VR. That was something that we worked on for like more than a couple of years. And then we were like, okay, finally we know how this works. And we know like how much of the computation would have to be dedicated to this. And we know how complex of a virtual reality environment we can create. So in the beginning, it was too computationally tasking, so that it was taken away from the visual complexity and beauty of a VR environment that you could create. So it was worthless to make a project out of it, because it wouldn't create a good result. But I mean, in terms of distribution of tasks, the way that we do it in the program, in the MArch2 program, is that we introduce everything to them equally, like ranging from digital fabrication to programming to VR as skills in the format of workshops in a 6-week-long summer session. So it's like bombarding all the students with all the information. And then what ends up happening is that people kind of take on roles naturally based on their own interests. So some people end up, doing more of the VR stuff, while others are taking more of the digital fabrication stuff, while others are taking more of the robotics stuff, and everybody ends up claiming a certain kind of expertise. And then they end up working together. So we go like, when you're forming your teams, make sure that you have one robotics person, one VR person, one whatever person, so that you are covered in terms of skills. And usually people do that, like it kind of naturally forms that way. We form the teams for the first quarter ourselves as faculty, and then afterwards we let the students deal. But I mean, the advantage is that it's like a 1-year-long program, so everybody's like studying with me. Like, I have like 35 students this year. Every studio that they're taking is with me for the full year. So that, and also their additional seminars that they're taking are technology seminars that are designed to support the studio. So whatever skill that I consider is relevant, I can design a smaller package seminar where they learn that skill, and then they can apply that skill in a more design-related context in the studio. So in a way, the program is kind of designed to make that happen to a certain extent. But I mean, based on the people that graduated, like some people end up working in industrial robotics while others are like doing VR projects in gaming companies, while others are working in traditional architecture offices. It really varies on what they ended up, focusing on throughout that year.
Thank you so very much for
Thank you for having me.
research with us.